Okay. Um, so if we look at a piece of steel, a tube of steel. So we have a tube of steel that we're going to look at. A cylinder of steel, a long rod of steel. And we're going to apply to it a load, an equal and opposite load on each side. So we're going to hang a load off the bottom and we're going to constrain it at the top. And that load we'll call up a point load P. Under that point load P, we are going to get some kind of deformation of that piece of steel. So that steel will extend by an amount that we're interested in, this amount here. And we're going to call that extension the Greek letter delta, for a difference or a change in, and then we want to make that a change in length. So if you imagine that this was originally L long, we will call that change in length delta L. Okay? So we can see that if you have a piece of material, steel in this case, if you apply a load to it, it will extend by an amount which we will call delta L. Now they're just conventions. We just use this Greek symbol delta to explain that it's a difference in length or a change in length. The two symbols, Greek symbols for delta, the Greek letter D, if you like, are delta and capital, so lowercase delta and capital delta, and they are both commonly used to indicate a change in something. So we're going to indicate a change in length here. Okay. Now, for different values of P, different values of this load, we will refer to them as P subscript 1, P subscript 2. And all that is a convention to say that we're talking about 2-point loads, P, and it has two distinct values. The first one we're going to call P1 and the second one we're going to call P2. Okay? So under a load P1, we will get a deflection delta L1, and then under this different load P2, we will get delta L2. Okay? That is the convention that we're going to use when we're looking at this problem here. Okay? Such that if P2 is greater than P1, and in fact P2 is greater than P1 to the extent that P2 is twice P1, we can represent that as P2 is equal to 2 times P1. And we don't have to put a mathematical symbol in here. If that's omitted, then we're assuming that we're multiplying. So 2P1 is by convention taken to mean 2 times P1, which we can either write that as 2 times P1, or we can sometimes write that as 2 dot P1. Okay, 2 times P1. All those by convention mean 2 lots of P1. So P2 is equal to twice the amount that P1 is. Okay. Now, for this particular piece of material here, we could increase P1 to P2, and we would find that in this particular experiment that we conduct, that delta L changes by if we double the point load P, we will find that we'll also double the change in length, so that this value here, if we have a P2 now, I've not drawn that very well. Let's redraw that. So we now have P2, which is twice P1. So P2 is represented by the delta. So that's delta. Let me get these back to. So delta L1 corresponds with a value or a force P1. For a force P2, let's just get rid of this. So if we now have a force P2, we find that we get an extension delta L2. And we find that the change in length for the second, that corresponds with the second load, because we've doubled that load, we find in this case that we are doubling the extended length. So if we pull twice as hard, we get twice the amount of extension. Okay. And we can represent that on a set of axes such that we can represent the force that we are pulling with on this axis and the change in or the length of the sample that we are looking at. If we just change this to the change in length delta L, because that's what we're interested in. We're interested in this extra length here and this extra length here. We find that let me just show what delta L2 is. Delta L2 is this dimension here. Okay, so that is delta L2. And this is delta L1. Okay. Going back to represent those on our set of graphs, if we have P1 at this level here, P subscript 1 is here, and then we've got twice P1, so that's P2, and we see here that P2 is 2 lots of P1. If our origin, so our 0 point, is at this point here, we find that under P1 we had a change in length delta L1, which corresponds to this point here. And then under P2 we found that we had delta L2, which was twice delta L1. Okay. And we found that to be a point at this point here, such that if we draw a line through those points, we find that this is what we say, or we can see that this is, roughly speaking, if I draw neatly, is a straight line. So we say that this has a linear relationship. So P1 has a linear relationship to the change in length delta L. Okay, so the force P that we apply has a linear relationship to the change in length.